These two vectors are fixed. All that I need is two numbers to describe all the vectors there, right? The moment you fix the basis. That's why it's interesting and useful. Okay, now what is the next step? So you have V1 corresponding to the max eigenvalue. So what will be the next step? Let's say if you want rank 1 approximation of your S, right? Sigma, so look at the max eigenvalue, lambda max V1 is one rank 1 approximation of S, right? What is rank 2 approximation of S? I have to consider both, right? So what will be the problem that I'm going to look at? Again, the same thing, V transpose SV. I want to maximize overall V subject to, of course, I want this V to be unit norm. I cannot stop here, right? At the moment I stop here, I'll get the same solution as before. What should be the second constraint? This should not be in the span of V1, right? I have already found out V1. So it should be, right? It should be orthogonal to V, right? The reason why I'm saying all this is, you should be able to understand how to pose a problem, right? In data analysis rather than just solving it. That's what optimization teaches you, how to solve it, right? So what do you think is the solution of this? V star is V2, right? V2 is what? The eigenvector corresponding to the second largest eigenvalue. Well, we will study optimization. We will understand how to get these things in a formal way using optimal, whatever, duality principles. But for now, there are other ways to prove, right? You can use eigenvector eigenvalues to prove this, right? So you got this, right? What is rank 2 approximation of the matrix? I mean, if you want to just look at two-dimensional, you want to come up with a two-dimensional space where you want to say most of the data lies, it's basically V1, V2, right? Span of V1, V2, or along the direction lambda 1, V1 and lambda 2, V2, right? These are the directions. It has the maximum component, right? So what will be the, let's say, ith solution? You just do this, right? Again, you do max overall V transpose SV subject to norm of V is 1, and instead of V1 transpose V equal to 0, you say Vi or Vj transpose V equal to 0, J equal to 1, 2, 3, etc. I minus 1, right? Because the ith step. This is the ith rank approximation of the matrix, right? So you are looking at I-dimensional subspace, right? This is how you do. This is essentially principal component analysis, right? What is principal? It's like main or important component, right? The first important component is V1, the second important component is V2, and so on. That's what we have looked at here. Okay? Is this fine, everyone? Right? Well, what is the solution of this? Well, the solution here would be Vi. Right? This is the solution. Okay? Right? Okay, let me ask you one more. Any questions? I can pause for a minute. We will look at the next problem. I'll ask you to propose a problem rather than solving it. Okay.
Sir? No, sir?
Yes, yes.
Sir, why is V transpose V 0? Can you explain that again?
V1 transpose V, right? See, you have already found out the first principal component, which is V1, right? If you don't consider this constraint, then it falls back to the previous problem. You will always say V1, right?
Okay, got it.
So I want it to be in the orthogonal direction. It should not be in the span of V1, right? And similarly, the fourth optimization problem, it should be orthogonal to both V1 and V2. In other words, you should not be in the span of V1, V2, right? And so on. Did I answer your question?
Yes, sir, yes.
Any other questions?
So do we first calculate the eigenvalue and vectors and then propose this max V transpose SV?
No, basically the intuition is first problem or this particular problem says basically we are trying to find what is the principal component here, right? The first principal component. It turned out to be the eigenvector, that's all. So essentially, in doing this process, you figured out that the eigenvalue decomposition is very, very important. Okay,
Yes,
is
sir.
that fine?
Yes, sir. So, suppose if I try to approach this problem this way, that I find the means the way that we find normal eigenvalues and vectors, and then choose suppose the first one or two eigenvalues which is greatest among them. Will this
Exactly.
work?
Yeah. Yeah. So essentially, if you have this S matrix, I ask you to find, let's say, the rank 3 approximation of this particular matrix. It will be something like this. This will be the rank 3 approximation of this matrix. Okay, rank 3. That means among all possible matrices of rank 3, which one will have, which is in some sense closest? The answer turns out to be this particular matrix. Okay, of course you have to match the dimension, you have to put zeros for others, that's a different thing, but apart from zeros this will be the match. Is that fine? So I can always stack zeros and complete the matrix, right? So it doesn't matter. Is that fine?
Yes, sir. Thank you, sir.
Yeah. So essentially, let's look at another problem now. Okay, so this is problem 2. Right. So let's say I want to classify things, right? If I want to classify, for example, let's say now let's look at reducing things itself. So now let's say you have one class which is class A, right? And you have another class which is class B. And these are the points that are labeled, and it's in very high dimensional space. Again, D is very large. Now I don't want to deal with, let's go back to the original problem of, I don't want to deal with D numbers. So what do? I bring that down to lower dimensional space, right? I'll also bring this to lower dimensional space. Now I have to bring this to lower dimensional space in such a way that, of course, I have to use the same matrix to bring it down. Okay, same projection matrix. But I should ensure that even in the lower dimensional space, I should be able to classify them, right? So what do you think is the problem that you will pose? Let's say you have these data, right? So x1, this is the data. Okay, so I'll write the problem clearly. So this is the data: x1, y1, x2, y2, and so on, xn, yn. So yn can be, or yj can be either -1 or 1. Think of -1 as spam and 1 as, or -1 as non-spam and 1 as spam, or any classification, right? So if this is the case, these are called labels, right? And this particular learning procedure is called supervised learning. So now given x1 through xn, right? So I want to project it onto lower dimension, yet I should be able to find, make sure that they're far off. So how do you ensure that this is achieved? What is the problem that you will solve? Or okay, so I'll also say yj could be in R if you are looking at some regression problems, right? You might be looking at some regression problem like house pricing and so on. It doesn't matter. Okay, so now how do you find, what is the problem that you will pose? What is the problem? How do you do that? So if they are far here, right, these two things, you should remain far here also, right? So how do you ensure that? How do you ensure? Yes, how do you ensure that if they are far in the higher dimension, when you go to the lower dimension, you should be far again? So what do you think is the problem that you will pose? Huh? Same norm. Meaning? So, for example, you take this to this, right? So, how do you do that? Suppose this is x. What is this? How do you represent this?